Lie down gently and allow your breathing to settle into a steady rhythm, letting the weight of the day release its hold. Close your eyes, letting the darkness behind them soften as the sound of the narration becomes the only movement around you. This is your space to drift, to listen, and to let the calm of quiet understanding settle in. What first compelled humanity to look up at the moon and wonder whether one day the boundary between Earth and that distant, pale surface could be crossed? The question lingered across centuries of skywatchers who charted its motion with increasing care, long before the possibility of travel existed. As the story unfolds, its truth emerges not from myth or imagination, but from the long chain of observations and measurements that eventually made the moon landing a scientifically achievable milestone. Early scholars measured the moon's steady progression across the sky with careful attention, noting how its phases corresponded with predictable cycles. They treated each shift in brightness not as a mystical sign, but as a physical pattern governed by the alignment of Earth, Moon, and Sun. Clay tablets from Mesopotamia recorded the moon's monthly path with remarkable consistency, capturing data that allowed later astronomers to refine calculations of its orbital period. Across the world, in ancient China, astronomers compiled lunar charts that highlighted eclipses and nodal crossings, demonstrating awareness that the moon's path was not random, but followed mechanisms that could be understood through repeated observation. Over time, those early records provided a base from which more precise scientific interpretations developed. As instruments evolved, scholars recognized how the varying angles of sunlight on the lunar surface shaped the contrast between bright highlands and darker mare regions. By comparing observations across seasons and locations, they built confidence that the moon's visible markings remained constant, revealing a solid, stable body rather than an ever-changing celestial apparition. These observations established a foundation that later allowed astronomers to infer topographical features, long before telescopes provided direct clarity. When early telescopic astronomy began, the moon became one of the first objects studied with magnification. Through Galileo's observations in the early 17th century, its surface revealed mountains, craters, and shadows that shifted predictably with the angle of sunlight. The sharp contrast on the terminator line demonstrated that the moon was not a smooth or polished sphere, but a textured world with measurable elevations. Scientists used the length of shadows cast by peaks to estimate their height, confirming that the moon possessed physical characteristics comparable in scale to terrestrial landscapes. This shift from viewing the moon as a purely symbolic object to a tangible, measurable place marked the first major scientific reorientation toward the idea that humans might one day reach it. As telescope designs improved, astronomers charted lunar coordinates with increasing accuracy, creating detailed maps that identified craters, mare regions, and highland plains. These maps served as reference points for centuries, allowing researchers to track even small variations in libration, the gentle oscillation that reveals slightly more of the lunar surface over time. Understanding these patterns became essential in the modern era, as they informed the precise targeting required for spacecraft navigation and landing. By the time spaceflight engineering emerged, scientists already possessed a refined understanding of the moon's size, mass, density, and gravitational influence. thanks to centuries of careful measurement and mathematical modeling. Out of this long observational history grew the confidence that landing on the moon was not a fantastical idea, but a problem that could be solved with the right combination of physics, engineering, and coordinated effort. The steady accumulation of data, lunar distance measurements, orbital parameters, gravitational perturbations, created a detailed portrait of the moon's behavior within the Earth-Moon system. This knowledge would eventually become the backbone of mission planning, enabling engineers and astronauts to predict trajectories, calculate fuel requirements, and design guidance systems capable of navigating the narrow margins required for a successful landing. As the 20th century approached, the accumulation of lunar knowledge intersected with rapid advances in physics, creating an environment where engineers could finally imagine moving beyond theoretical curiosity. The laws governing motion, gravity, and propulsion were no longer abstract concepts, but practical tools that could be applied to machinery capable of leaving Earth's surface. The groundwork laid by physicists who explored momentum, energy transfer, and orbital dynamics began to shape the earliest calculations for vehicles that might someday reach beyond the atmosphere. The emergence of liquid-fueled rocketry provided the first real proof that controlled ascent into space was physically possible. Engineers studying combustion, thrust efficiency, and nozzle design recognized that by sustaining acceleration beyond the point where atmospheric drag dominated, a craft could enter the smooth arc of orbit. Each improvement in engine stability and propellant handling created a clearer path toward the speeds required to escape Earth's gravitational hold. These steps, though incremental, moved steadily toward the domain where lunar travel could be treated as a solvable engineering problem rather than an unreachable aspiration. As research expanded, attention turned toward the challenge of guiding a vehicle through the vacuum of space with precision. Scientists refined methods for predicting orbital paths, using increasingly accurate measurements of gravitational influence and mass distribution. The moon's distance, once estimated with rough instruments, became known with tight margins thanks to optical surveys and radar ranging. Understanding its subtle orbital variations allowed mission planners to anticipate how a spacecraft would need to adjust its trajectory during the long coast between Earth and lunar orbit. This depth of knowledge ensured that future missions could align their approach with the quiet precision required for a safe arrival. Meanwhile, the study of the lunar surface advanced through improved telescopic imaging and photographic techniques. Observers captured sharper views of crater arrangements, mare boundaries, and slope gradients, allowing scientists to produce detailed atlases of the near side. These maps revealed regions with smoother terrain, making them promising sites for an eventual landing. The consistency of the observed features over time reinforced the understanding that the moon's surface remained geologically inactive on human timescales, offering stability that mission designers could rely upon when considering where astronauts might set foot. The scientific community also focused on understanding the moon's gravitational field, recognizing that variations in mass beneath the surface could subtly affect orbiting spacecraft. By measuring small deviations in the motion of probes and lunar orbit calculations, researchers inferred the presence of mass concentrations that would later influence landing trajectories. Knowing where these anomalies existed allowed mission designers to avoid regions where gravitational irregularities might complicate navigation, further refining the approach to a feasible lunar descent. These developments formed an interconnected foundation: the physics of motion, the engineering of propulsion systems, the mapping of the lunar surface, and the precise measurement of distance and gravitational influence. Together, they created a comprehensive framework that made the idea of traveling to the moon not only conceivable, but practical. Long before rockets rose from launch pads or astronauts trained for the journey, this body of knowledge established the conditions in which such a mission could take shape. With each scientific advancement, the moon moved a little closer, not in distance, but in accessibility, transforming from a distant companion in the night sky into a destination defined by measurable parameters and achievable objectives. As engineering knowledge matured, the possibility of navigating beyond Earth's bounds began to shift from theory into planned experimentation. Laboratories focused on the specific demands of high-altitude flight, examining how materials behaved when exposed to thermal extremes and rapid acceleration. Engineers refined alloys capable of withstanding both structural stress and intense heating, knowing that any vehicle intended for lunar travel would confront these challenges repeatedly. During ascent, while coasting through open space, and again upon returning through the atmosphere, attention soon centered on guidance technologies, since precision mattered as much as raw power. Inertial navigation systems, originally developed for aircraft and submarines, evolved into sophisticated assemblies of gyroscopes and accelerometers capable of measuring movement without external reference points. These systems allowed calculations of a spacecraft's position and velocity with remarkable accuracy, making it possible to chart a path toward the moon even when radio contact was interrupted. As designers improved stability and reduced drift, mission planners gained confidence that a spacecraft could maintain its intended course for the entire journey. Communication networks grew alongside these innovations. Engineers recognized the spaceflight demanded uninterrupted data flow between Earth and the vehicle, prompting the construction of ground stations across multiple continents. Their arrangement allowed tracking antennas to maintain contact with the spacecraft as Earth rotated, ensuring that no part of the mission relied on guesswork. The continuous stream of telemetry, temperature readings, pressure levels, thrust data, electrical output created a real-time portrait of the craft's condition, enabling swift adjustments whenever necessary. This global coordination became one of the essential underpinnings of lunar operations. The development of life support systems added another layer of complexity. Designers needed to create controlled environments capable of maintaining breathable air, stable temperatures, and reliable removal of carbon dioxide. Understanding the physiology of human adaptation to confined spaces, microgravity, and radiation exposure guided these refinements. Engineers built sealed cabins that recycled air through chemical absorbers and regulated humidity through carefully managed condensation processes. These systems had to function with absolute reliability, as even small fluctuations could become critical when astronauts traveled far beyond rapid rescue capability. With these components advancing in parallel, researchers refined calculations related to orbital transfers, Plotting a trajectory from Earth orbit to lunar orbit required a precise balance of velocity, timing, and alignment. Mission planners studied how the moon's position changed hour by hour, determining launch windows where the spacecraft could efficiently intersect its path. The mathematics behind such maneuvers relied on well-established laws, yet executing them demanded exact engineering performance. As tests confirmed that propulsion systems could deliver the necessary impulse at the right moment, confidence grew that a crewed mission was technically within reach. All of these efforts converged to create a coherent foundation for the lunar program. Each breakthrough, structural, navigational, environmental, or mathematical, filled another piece of the broader framework needed to carry humans across the 250,000 miles of open space. Nothing about the process occurred in isolation, and every refinement strengthened the feasibility of the next step. By the time the first dedicated lunar missions were planned, the essential principles had already been validated through extensive research, providing a stable platform from which the journey toward the moon could finally begin. When preparations for actual space missions intensified, the focus expanded from designing components to validating them through methodical testing. Engineers subjected every subsystem to conditions that mimicked the extremes of space as closely as possible. Vacuum chambers allowed them to observe how electronics behaved without atmospheric insulation, revealing the need for careful thermal management to prevent overheating or uncontrolled cooling. Vibration tables replicated the forces produced by rocket engines during liftoff, ensuring that wiring, seals, and structural joints could endure the stress without failing. Each test refined the understanding of what a spacecraft would experience beyond Earth, narrowing potential points of weakness before astronauts ever boarded a vehicle. As the testing matured, researchers turned to the challenge of re-entry, a phase that required careful analysis of aerothermodynamics. Returning from the moon meant entering Earth's atmosphere at far higher speeds than those experienced by low Earth orbit flights. To manage this, scientists studied how plasma formed around high-velocity objects and how heat distributed across protective surfaces. They developed ablative materials that slowly vaporized under extreme temperatures, carrying heat away from the capsule. Engineers documented how these materials eroded under specific loads, creating predictive models for how the heat shield would behave during an actual mission. Understanding these interactions allowed them to calculate margins that protected both the spacecraft's structure and the crew within it. Parallel to these technical developments, mission planners refined the sequence of operations needed for lunar travel. Every stage required detailed timing: launch, Earth orbit insertion, translunar injection, mid-course corrections, lunar orbit braking, descent, ascent, and the journey home. They mapped these steps against precise gravitational models to avoid inefficiencies that could consume too much fuel. By analyzing numerous simulations, planners determined how small deviations early in the mission could influence conditions thousands of kilometers later. From this work emerged highly disciplined procedures that astronauts would follow, ensuring that each maneuver aligned with the physics governing the spacecraft's path. Training programs emerged to prepare astronauts for these sequences. Simulators recreated the motions and responses of the spacecraft in real time, feeding pilots information based on accurate physics models. In these sessions, astronauts practice navigating using instrument panels identical to those in the actual vehicle, learning how small adjustments influence trajectory and orientation. Neutral buoyancy tanks and specialized rigs help them rehearse the physical demands of maneuvering in low gravity, reinforcing spatial awareness in an environment where traditional cues lost relevance. The training emphasized repetition not for memorization alone, but to cultivate instinctive handling of complex procedures under varying conditions. As all of these elements came together, early test missions without crews paved the way for later milestones. Uncrewed flights verified that propulsion systems performed as predicted during the long coast to the Moon. Tracking stations observed how spacecraft responded to the gravitational pull of both Earth and the Moon, confirming the accuracy of planned trajectories. Telemetry relayed information about temperatures, radiation exposure, and onboard system behavior, providing engineers with extensive data for refinement. These early missions also assessed communication reliability across vast distances, demonstrating the signals could travel between Earth and the spacecraft without significant degradation when properly supported by ground infrastructure. By the time humans were scheduled to make the voyage, the foundation had been reinforced through years of empirical data, calculated predictions, and rigorous validation. Every major risk had been studied in detail, and the systems designed to manage those risks had undergone repeated trials. The moon landing would not be an act of trial and error, but the culmination of countless interlocking efforts, each grounded in measurable evidence and shaped by a thorough understanding of the physical laws that governed the journey. With these preparations in place, the threshold between planning and execution finally narrowed, allowing the mission to move from concept into reality with a confidence built on cumulative scientific achievement. As the program advanced towards sending a crew to the lunar surface, attention shifted to integrating every component into a unified operational system. Engineers examined how the spacecraft's modules interacted, confirming that electrical connections, hydraulic lines, and control pathways functioned without interference. The command module, lunar module, and service module each carried specialized responsibilities, yet all needed to operate as a cohesive whole. Through extensive simulations and full-scale rehearsals, teams verified that power distribution remained stable when loads changed abruptly, that guidance computers could synchronize data between modules, and that manual controls responded consistently in any configuration. These evaluations ensured that astronauts would encounter a predictable environment, even as the mission transitioned through very different phases. During this stage, researchers scrutinized the behavior of the guidance computer, which served as the analytical core of navigation. Its algorithms performed thousands of calculations per second, evaluating acceleration, orientation, and velocity vectors. The system compared live inputs with the program trajectory, adjusting thrust commands as necessary to maintain alignment with the intended path. Engineers tested how the computer handled noisy data, confirming that it could filter out anomalies produced by minor sensor fluctuations. As reliability improved, mission planners could trust that the spacecraft would consistently interpret the surrounding conditions and translate them into accurate navigational outputs. The refinement of the lunar module demanded special care, because its purpose differed fundamentally from that of the other components. Designed exclusively for operation in vacuum, it required lighter materials, thinner walls, and landing structures capable of absorbing impact forces on uneven terrain. Researchers analyzed how its descent engine throttled, ensuring that thrust could be modulated smoothly as it approached the surface. They measured how the guidance radar locked onto the terrain, confirming that it could detect altitude and descent rate with enough precision to support safe navigation. The vehicle's ascent engine underwent equal scrutiny, since it had to ignite reliably in lunar gravity with no backup system to replace it. Each successful test strengthened confidence in the module's ability to transport astronauts between orbit and surface without unexpected behavior. Communication protocols also became more sophisticated as the lunar phase approached. Engineers studied how radio waves interacted with Earth's ionosphere at different times of day, adjusting antenna configurations to maintain signal clarity when conditions fluctuated. They quantified the delays inherent in long-distance transmissions, so mission control and crew could synchronize actions despite the round-trip light time between Earth and the Moon. Audio channels were separated from telemetry streams to prevent cross-interference, ensuring that critical engineering data never masked spoken communication. These refinements preserved the integrity of both routine updates and emergency instructions, forming a stable backbone for all exchanges during the mission. The study of the lunar surface continued to evolve, supplying essential information for landing site selection. High-resolution photographs from orbiting spacecraft revealed subtle gradients, loose regolith patterns, and crater distributions invisible from Earth-based telescopes. Scientists evaluated how light struck the surface at different times of the lunar day, identifying angles that minimized harsh shadows, which could obscure hazards during descent. They assessed the reflectivity of the terrain to understand how it might affect guidance sensors relying on optical feedback. By combining geographical mapping with illumination studies and soil analyses, the team pinpointed regions where mechanical contact with the surface posed the least risk. Every refinement contributed to a growing sense of readiness. The interplay between physical science, engineering precision, and operational planning produced an increasingly complete picture of what astronauts would encounter at each stage. The program relied not on a single breakthrough, but on a cumulative series of verifications, each confirming that the system as a whole was prepared for the demands of a lunar landing. With each successful test, the distance between planning and execution diminished, leaving only the final steps before sending humans to a world no one had ever touched. With the mission architecture firmly established, teams began refining the launch sequence with exceptional precision. The Saturn V, towering above its support structures, required meticulous attention to ensure that each stage functioned in flawless succession. Engineers calibrated its engines to deliver a predictable thrust curve, studying how temperature, fuel composition, and turbopump performance influenced stability during ascent. The entire stack was assessed for structural resonance, because even minor oscillations could propagate through its frame and affect instrument readings. Through repeated evaluations, specialists confirmed that the rocket could lift the combined mass of the spacecraft into orbit while preserving the accuracy of its guidance systems. As the launch vehicle matured, mission controllers turned their focus to the choreography of in-flight procedures. The moment the rocket cleared the tower, a series of events unfolded in rapid order: roll programs, pitch adjustments, staging intervals, and engine shutdown points. Controllers synchronized these actions with radar tracking to verify that the vehicle was following the expected trajectory. Data poured into monitoring consoles at mission control, creating a real-time portrait of mechanical performance and environmental conditions. Analysts watched for deviations from anticipated patterns, ready to recommend adjustments if a sensor reading appeared inconsistent or an engine parameter drifted toward a threshold. Transitioning from the intensity of ascent into Earth orbit required another layer of precision. Once the spacecraft reached the designated altitude, systems stabilized and the crew prepared for the next critical operation: translunar injection. This maneuver demanded a finely tuned burn from the upper stage, providing the velocity necessary to escape Earth's gravitational well and begin the long coast toward the Moon. Engineers calculated the timing down to fractions of a second, ensuring that the burn aligned with the spacecraft's orientation and the Moon's orbital position. Any misalignment would have forced significant corrections later, consuming valuable fuel reserves. Extensive rehearsals and simulations allowed mission planners to anticipate these variables and adapt the timing as new data became available. Once on the translunar trajectory, the environment around the spacecraft changed noticeably. Gravity's grip weakened, and the vehicle settled into a state of continuous freefall toward its distant target. Although serene on a physical level, this phase demanded steady scientific attention. Instruments measured radiation levels, solar wind intensity, and micrometeoroid activity, providing insight into the space between Earth and the Moon. Telemetry confirmed that thermal regulation systems were evenly dispersing heat across the spacecraft's surfaces, preventing localized hotspots or excessive cooling. Navigation teams monitored the craft's orientation, using star trackers and inertial sensors to confirm that it remained aligned with the intended path. Mid-course corrections formed an essential part of this long transit. Even small irregularities, variations in thrust, slight sensor drift, or gravitational influences from celestial bodies could shift the spacecraft's trajectory over thousands of kilometers. By analyzing subtle deviations in velocity and position, controllers could command brief engine burns that adjusted the spacecraft's line of travel. These changes required careful execution. Too strong a correction risked overshooting the target, while too weak a burn might not compensate for accumulated drift. When performed successfully, each adjustment refined the trajectory, ensuring that the spacecraft approached the Moon's sphere of influence along the desired corridor. As the vehicle neared its destination, the dynamics of the journey shifted once more. The Moon's gravity began to assert itself, gradually taking control of the spacecraft's motion. Mission planners relied on gravimetric data to calculate the point where a braking burn would slow the craft sufficiently to transition into lunar orbit. This maneuver demanded accuracy, not just in timing, but in orientation, requiring the spacecraft to pivot so the engine thrust opposed its forward momentum. Data from the guidance system confirmed alignment, while tracking stations monitored the evolving orbital shape. When the burn concluded, the spacecraft drifted into a stable path around the Moon, completing one of the most delicate navigational transitions of the mission. From this vantage, the lunar surface appeared in sharp detail, revealing the textures and gradients previously studied through remote sensing. Orbit allowed for continued assessment of the chosen landing region, guiding final decisions about the descent sequence. Engineers compared real-time measurements with pre-mission maps, noting how subtle changes in lighting or surface conditions might influence the upcoming approach. The spacecraft's onboard systems verified that the lunar module was fully operational, checking pressure levels, battery charge, docking mechanisms, and propulsion readiness. By the time preparations for separation began, every component had been analyzed repeatedly, supporting a smooth progression into the next phase of the journey. The separation of the lunar module marked a pivotal moment in the mission. Once undocked, the module became an independent spacecraft with its own propulsion, guidance, and life support systems. Engineers had ensured that its mass distribution, center of gravity, and engine thrust were calibrated for precise maneuvering, enabling controlled descent toward the lunar surface. Every component was monitored as the module began its trajectory, with telemetry confirming fuel flow, engine performance, and system stability. The crew relied on instruments designed to provide continuous feedback on altitude, velocity, and horizontal displacement, integrating data to maintain a smooth and controlled approach. Descent itself involved a combination of automated control and human oversight. The descent engine could modulate thrust dynamically, compensating for irregularities in the surface and variations in gravitational pull. Guidance radar measured the distance to the ground, providing real-time input for rate of descent calculations. By observing these readings, the crew adjusted the vehicle's pitch and roll to ensure alignment with the predetermined landing site. Subtle adjustments were made to correct for lateral drift caused by minor orbital variations or residual momentum from the undocking maneuver. The goal was not speed but precision, a controlled, gradual reduction of velocity that allowed the landing pads to meet the lunar regolith without sudden shocks. The lunar surface itself presented unique mechanical challenges. Fine, powdery regolith, formed over billions of years from micrometeorite impacts and surface weathering, covered uneven basalt plains and scattered craters. Engineers had studied its bearing capacity to design landing gear capable of dispersing weight without sinking excessively. The module's pads were structured to absorb impact forces while maintaining stability, preventing tipping or sliding. Visual and radar observations guided the crew to a relatively flat area, reducing the risk of contact with rocks or slopes. Every meter of descent was accompanied by data from onboard sensors, allowing instantaneous corrections that translated centuries of lunar study into tangible safety measures. Upon touchdown, instruments verified the stability of the module. Sensors measured pressure on the landing pads, the orientation of the craft, and vibrations transmitted from the surface. Confirming these parameters ensured that the structural integrity remained uncompromised and that life support systems continued to operate within expected norms. Only then could astronauts begin preparations for extravehicular activity, a phase meticulously planned to account for environmental hazards such as temperature extremes, solar radiation, and the vacuum of space. As astronauts emerged from the cabin, their suits served as miniature life support systems. Each layer regulated temperature, provided oxygen, removed carbon dioxide, and maintained pressure. Helmets offered clear visibility while shielding eyes from solar glare, and communication systems relayed every movement back to mission control. Tools were carefully organized for the collection of lunar samples, deployment of scientific instruments, and placement of retroreflectors used for precise laser-ranging experiments. Every action taken on the surface was grounded in pre-mission calculations and material science studies, ensuring that human interaction with the Moon did not compromise either safety or data integrity. Scientific work on the surface included gathering rock and soil samples, documenting terrain, and deploying instruments such as seismometers and magnetometers. Lunar rocks were examined for mineral content, composition, and age, providing direct evidence of the Moon's geological history. These analyses revealed patterns of volcanic activity, impact cratering, and regolith formation, confirming hypotheses derived from remote sensing and earlier laboratory studies. Instruments left on the surface transmitted data over time, extending the observational reach of Earth-based laboratories and allowing continuous monitoring of lunar conditions long after the astronauts departed. After completing their surface activities, the crew prepared for ascent. The lunar module's ascent engine ignited to lift the astronauts back into orbit, where precise rendezvous with the command module awaited. Every calculation, thrust angle, burn duration, and velocity increment was executed according to pre-validated simulations. The guidance system continuously corrected minor deviations, and instrumentation monitored acceleration, fuel consumption, and trajectory. Successful docking ensured the safe transfer of crew and samples, allowing the spacecraft to commence its return to Earth along a carefully calculated re-entry path. During the return journey, the spacecraft re-entered the domain of Earth's gravity, requiring careful attention to re-entry angles and heat shield performance. Calculations predicted how atmospheric friction would generate extreme temperatures, and ablative materials absorbed and dissipated this energy to maintain cabin integrity. Telemetry confirmed that the structural and thermal systems functioned as designed, while tracking stations monitored descent from multiple angles. Splashdown occurred at a predetermined location where recovery teams awaited to retrieve the crew and spacecraft. Each stage, from launch to splashdown, represented the culmination of decades of observation, measurement, and meticulous engineering. Beyond the immediate mechanics of the mission, the collected data continued to enrich scientific understanding long after the astronauts returned. Lunar rocks and soil were catalogued, analyzed under microscopes, and subjected to chemical assays that revealed their precise mineral composition. Radiometric dating techniques determined their ages, confirming a chronology of lunar events that spanned billions of years. These findings validated theories about the Moon's formation, its volcanic activity, and the accumulation of regolith through countless micrometeorite impacts. Each sample represented a tangible record of processes that had unfolded far from Earth, offering insight into planetary evolution in a broader context. Seismometers and other instruments left on the surface provided continuous streams of information, detecting moonquakes, tidal flexing, and meteorite impacts. Analysis of seismic waves allowed scientists to infer the internal structure of the Moon, revealing the thickness of its crust, the composition of the mantle, and the presence of a small, dense core. data collected over time created a three-dimensional understanding of the Moon's interior, information that could not have been obtained without direct placement of sensitive equipment. These observations enhanced models of lunar geophysics, contributing to more accurate predictions of surface behavior and potential hazards for future missions. Optical and laser-based experiments conducted on the Moon's surface produced results that reached far beyond the immediate mission. Retroreflectors placed during the expedition reflected laser beams sent from Earth, allowing precise measurement of the distance between the two bodies. Repeated measurements over years confirmed not only the Moon's orbital parameters, but also its gradual recession from Earth at a rate of approximately 3 centimeters per year. These experiments offered concrete, ongoing verification of gravitational models, tidal interactions, and long-term dynamics of the Earth-Moon system, transforming theoretical predictions into measurable reality. The photographs captured during the mission served as another layer of empirical evidence. Detailed images documented the texture and topology of the lunar surface, showing the distribution of craters, boulders, and regolith layers. Shadows cast by surface features demonstrated the principles of illumination and perspective, while juxtaposition with pre-existing orbital imagery verified both accuracy and consistency. These photographs became reference points for subsequent missions, enabling refined mapping and navigation, while also serving as an independent record confirming the physical presence of human activity on the lunar surface. In addition to the immediate scientific harvest, the mission influenced the development of technology across multiple disciplines. Computational systems refined for navigation and data analysis contributed to advances in control theory, real-time monitoring, and software reliability. Material science evolved through the testing of high-strength alloys, thermal protection systems, and composite structures, influencing aerospace engineering, construction, and manufacturing. Sensors developed for life support monitoring and environmental assessment found applications in other extreme conditions, from underwater research to polar exploration, demonstrating the broader utility of innovations driven by lunar objectives. Observations of the Moon's influence on Earth were also refined through the mission's findings. Precise measurements of gravitational interactions, rotational dynamics, and tidal forces helped scientists understand long-term patterns in ocean behavior and climate modulation. By correlating these findings with geological records, researchers could trace subtle connections between lunar cycles and terrestrial phenomena. In this way, the moon landing provided more than local or temporary knowledge. It deepened comprehension of interconnected systems spanning Earth and its closest celestial neighbor. As the scientific community absorbed these discoveries, subsequent lunar missions built upon the foundation established by the first landing. Orbital surveys became more detailed, with instruments capable of detecting minute variations in topography, surface composition, and thermal characteristics. Robotic landers and rovers extended observational reach to regions inaccessible to human crews, while remote experiments leveraged technologies validated during earlier missions. Together, these programs confirmed the accuracy of prior measurements and expanded understanding of lunar geology, environmental conditions, and potential resources, establishing the moon as a subject of enduring empirical study. In reflecting on the journey, the moon landing can be understood as a synthesis of centuries of observation, experimentation, and incremental progress. Every measurement, calculation, and material innovation converged in a sequence of controlled, verifiable actions that transformed aspiration into achievement. The moon itself, once a distant point of wonder in the night sky, became a laboratory for rigorous science, a stage for controlled experimentation, and a source of knowledge extending far beyond the surface, touched by human feet. It remains, in every measured way, a testament to the capacity of human inquiry, guided by observation, analysis, and precision. The legacy of the mission extends beyond immediate measurements to the continuous refinement of lunar knowledge. Subsequent orbital studies utilized increasingly sensitive instruments, revealing subtle variations in surface composition and elevation that were imperceptible during the first landing. Spectrometers analyzed reflected light across multiple wavelengths, allowing scientists to distinguish mineral abundances, identify basalt flows, and map subtle chemical gradients. Data from these instruments confirmed predictions made by geologists studying lunar rocks returned to Earth, providing a multidimensional verification that combined in situ sampling with remote sensing. Thermal studies also deepened understanding of the moon's environment. Sensors measured diurnal temperature swings, noting extremes that ranged from intense sunlight to the frigid absence of solar energy at night. By correlating these readings with surface material properties, scientists could model heat absorption and radiation across different lunar terrains. These models informed engineering considerations for future landers, habitats, and long-term instrumentation, ensuring that systems deployed on the moon could endure the severe oscillations in temperature without structural or functional compromise. Gravitational studies remained another area of insight. High-precision measurements of the moon's effect on orbiting satellites revealed localized anomalies in mass distribution, known as mascons, which subtly altered the trajectory of passing spacecraft. Recognizing these deviations allowed planners to adjust orbital paths for long-term satellites and future crewed missions, maintaining stability and predicting fuel requirements with increased confidence. Such data also illuminated aspects of lunar geology, suggesting concentrations of denser material beneath the surface and contributing to models of the moon's internal layering and formation history. The moon's regolith, a layer of fragmented rock and fine dust, continued to provide clues to the history of impacts and surface evolution. Detailed analysis of grain size, chemical composition, and layering patterns indicated processes of micrometeorite bombardment, space weathering, and solar wind implantation over billions of years. This information clarified the mechanisms by which the lunar surface had matured, revealing insights not only into the moon's past, but also into the broader processes shaping rocky bodies across the solar system. Comparative studies with meteorites and terrestrial analogues reinforced the universality of these processes in planetary formation. Seismic studies collected by instruments left behind offered ongoing insight into the moon's dynamic properties. Moonquakes, though less frequent and intense than earthquakes, revealed stress distributions within the crust and mantle. By mapping wave propagation, scientists deduced the material characteristics and density variations of subsurface layers, enhancing the understanding of structural mechanics in an environment with low gravitational stress. These measurements supported predictions about the moon's stability, informing the design of both robotic and potential long-term human installations. Reflecting on the broader significance, the moon landing acted as a calibration point for observational methods. Every instrument, every procedure, and every measurement executed during the mission and in subsequent analyses contributed to the refinement of scientific methodology. From laser ranging experiments to rock sampling, the data served as benchmarks, enabling future missions to design experiments with higher precision and reliability. In this sense, the moon landing became not merely an event in history, but a continuous reference framework anchoring lunar science to reproducible, verifiable data points that endure across decades. The influence of these scientific achievements reaches into fields far removed from lunar exploration. Remote sensing techniques developed for lunar observation have been adapted for Earth studies, from atmospheric monitoring to geological surveying. Materials and life support systems designed for survival in extreme lunar conditions informed engineering approaches for habitats in polar regions, submarines, and long-duration aviation projects. Computational methods refined for guidance and navigation continued to underpin autonomous systems, robotics, and real-time environmental monitoring across multiple disciplines. The moon landing, therefore, demonstrates how the pursuit of empirical knowledge can propagate innovations across a vast spectrum of human activity, each connected by rigorous observation and scientific validation. As instruments on Earth and in space continue to monitor the moon, its role as a laboratory persists. Each orbit, each laser pulse, and each spectral analysis contributes incremental understanding, verifying prior findings and revealing new nuances. The moon remains an active subject of scientific study, with the first landing serving as a foundation for decades of exploration. Every measurement traces a continuous line back to the disciplined efforts of engineers and scientists, illustrating the deliberate progression from observation to intervention, from prediction to confirmation. In this way, the moon remains both a destination and a record of systematic inquiry, where knowledge accumulates not through conjecture, but through sustained, verifiable exploration. In addition to scientific instrumentation, the precise mapping of the moon's surface has evolved steadily, producing increasingly detailed topographical models. High-resolution altimetry from orbiting satellites has measured elevation changes to a matter of meters, delineating crater depths, mountain heights, and the slopes of lava plains. These measurements allow mission planners to evaluate landing feasibility with unprecedented accuracy. Slope analysis and terrain roughness calculations, combined with prior knowledge from earlier landings, guide the positioning of future instruments and vehicles. Each refinement reduces uncertainty, ensuring that the moon's surface can be approached, studied, and traversed with predictability grounded in measurable evidence. The study of lunar magnetism provided another layer of understanding. Although the moon lacks a global magnetic field comparable to Earth's, localized anomalies persist within the crust, remnants of ancient magnetic activity. Magnetometers on orbiting satellites detected variations that correspond to specific geological structures, offering insight into the thermal history and composition of the interior. Analysis of these anomalies allows scientists to infer processes such as core cooling, crustal differentiation, and the persistence of magnetic minerals. These observations, verified through multiple missions, contribute to a comprehensive model of the Moon's geophysical evolution. Cosmic radiation and solar particle monitoring remain critical for both instrumentation and crew safety. Sensors deployed on the surface and in orbit quantify exposure levels to high-energy particles and solar wind, revealing patterns that fluctuate with solar cycles. Understanding these variations is essential for the design of protective shielding and for evaluating long-term effects on both humans and sensitive equipment. Data collected from these observations also informs broader studies of space weather, providing predictive insight into the behavior of solar emissions and their interaction with celestial bodies. Gravity mapping has further refined orbital mechanics for lunar satellites. Measurements of how the Moon's uneven mass distribution affects the trajectories of low-altitude orbiters enable precise calibration of satellite orbits. Knowledge of mass conlocations, combined with lunar surface mass density calculations, allows navigators to plan stable orbital paths for extended missions, minimizing fuel consumption while maximizing observational coverage. This precision supports not only continued scientific research, but also operational planning for robotic exploration and potential future human outposts. The Moon's exosphere, a tenuous layer of atoms and molecules surrounding the surface, has also been examined. While extremely thin compared to Earth's atmosphere, it exhibits detectable fluctuations influenced by solar wind, micrometeorite impacts, and surface outgassing. Instruments capable of analyzing these minute variations provide insight into particle sources, surface interactions, and long-term atmospheric dynamics. Studying the exosphere bridges the understanding of planetary environments, connecting the Moon's minimal atmospheric presence with comparative studies of other bodies in the solar system, from Mercury to asteroids. Long-term lunar observation has extended into the study of thermal inertia and regolith compaction. Instruments measure how the surface absorbs, stores, and radiates heat, offering insight into the properties of the fine particulate layer covering much of the Moon. These studies inform predictions about surface stability, dust movement, and thermal conditions that future missions must accommodate. Through these analyses, scientists gain a more complete understanding of how solar heating and surface composition interact, enabling accurate modeling of conditions across lunar day and night cycles. Every mission, instrument, and measurement contributes to a cumulative knowledge base that defines the Moon as an accessible, measurable, and scientifically rich environment. Each step, from orbit insertion to surface sampling, from seismic monitoring to magnetometry, reinforces the accuracy of previous findings while expanding the range of observable phenomena. The Moon, once a distant point of fascination, now exists as a domain thoroughly examined through empirical study, its features quantified, its dynamics understood, and its environment carefully characterized. Knowledge accumulated through these scientific efforts ensures that future endeavors can proceed with clarity and confidence, grounded entirely in observation, measurement, and reproducible evidence. Building upon prior measurements, spectroscopic analysis from orbit has provided a detailed inventory of lunar surface minerals. Instruments capable of detecting reflected light across ultraviolet, visible, and infrared wavelengths differentiate between silicates, oxides, and metal-rich regions. These observations identify variations in basaltic plains and highland materials, confirming geological interpretations derived from returned samples. By comparing spectra across multiple locations, scientists can map compositional diversity, tracing the processes of volcanic flows, impact melting, and space weathering over billions of years. Each data point corroborates laboratory analyses, ensuring a precise, reproducible understanding of lunar geology. The study of cratering continues to reveal the Moon's impact history. High-resolution imagery allows measurement of crater diameters, depths, and ejecta patterns. Analysis of overlapping craters and stratigraphic relationships provides a chronological framework for estimating the relative ages of different regions. Comparing these observations with impact models informs understanding of collision dynamics in the inner solar system. These studies also refine estimates of meteoroid flux over time, offering insight into the environmental conditions that shape both the Moon and Earth throughout their early evolution. Dust dynamics have become an area of careful monitoring. Lunar regolith is highly mobile when disturbed, capable of adhering to surfaces and forming fine clouds when particles are displaced. Experiments quantify how electrostatic forces, micrometeorite impacts, and solar radiation affect particle behavior. Understanding these dynamics is crucial for the design of equipment, habitats, and mobility systems intended for extended operations. By studying the interaction between surface dust and mechanical systems, scientists anticipate challenges and create solutions that minimize wear, contamination, and operational hazards. Lunar volcanism, while largely ancient, continues to inform scientific perspectives. Detailed mapping of lava flows, dome structures, and rills provides insight into thermal history and the composition of erupted material. Geochemical analysis of these features, alongside returned samples, allows reconstruction of volcanic episodes and the chemical differentiation of the Moon's interior. This information contributes to broader planetary science, illustrating how thermal evolution and magmatic processes vary among rocky bodies and influence long-term surface development. Seismological observations remain vital in assessing the Moon's internal activity. Although less frequent than terrestrial earthquakes, moonquakes illuminate stress distributions and structural behavior beneath the crust. By analyzing the propagation of these vibrations, researchers infer mechanical properties of layers, including elasticity, density, and fault boundaries. These studies inform not only basic geophysical models, but also practical considerations, such as site selection for future landers, the stability of long-term installations, and potential hazards associated with natural seismic activity. In addition to geological and geophysical data, studies of the Moon's environment continue to emphasize space weather interactions. Solar wind particles, micrometeorite impacts, and cosmic rays are monitored continuously, providing insight into how external energy sources affect surface composition and electronics. Measurement of particle flux and radiation dose informs both scientific understanding and engineering requirements for protective shielding. These studies also establish baseline environmental data, enabling the design of experiments and equipment that can survive repeated exposure to harsh conditions. The ongoing analysis of lunar orbital mechanics further enhances mission planning. Data collected from satellites and laser ranging experiments refine models of the Moon's orbit, rotation, and gravitational anomalies. These calculations provide the basis for accurate prediction of landing trajectories, satellite positioning, and mission timing. By continually updating these models with empirical measurements, planners maintain a highly reliable framework that guides both crewed and robotic operations. The Moon, though distant, is thoroughly mapped in its physical and dynamic properties, allowing exploration to proceed with confidence, anchored in precise science. Taken together, these strands of investigation, from mineralogy to seismology, from surface dust dynamics to orbital calculations, demonstrate a continuous, evolving understanding of the Moon. Every instrument, observation, and measurement contributes to an interconnected scientific framework. Each finding builds upon prior knowledge, creating a coherent picture that transforms the Moon from a remote celestial body into a well-characterized laboratory of planetary processes. The integration of these studies exemplifies the rigorous, methodical approach that defines modern lunar science, rooted in careful observation, repeatable measurement, and empirical validation. Investigations into the Moon's polar regions have revealed additional layers of complexity. High-resolution mapping and neutron spectroscopy indicate the presence of hydrogen-rich deposits in permanently shadowed craters, suggesting the accumulation of water ice over geological timescales. By measuring reflected neutrons and thermal emission, scientists estimate both the extent and depth of these deposits, providing empirical data for resource assessment. These findings carry implications not only for scientific inquiry into lunar history, but also for logistical planning, offering potential support for future crewed missions through in-situ resource utilization. Temperature monitoring across polar craters confirms extreme thermal conditions. Sunlight rarely reaches these regions, producing surfaces that remain near cryogenic levels for extended periods. Instruments record how thermal gradients fluctuate minimally, preserving the ice and creating stable environments, unlike the more thermally dynamic equatorial plains. Understanding these conditions is essential for the design of instrumentation and habitats intended to operate in low-temperature regimes. Materials must retain flexibility, structural integrity, and functionality under persistent cold, and electronic systems must remain responsive despite reduced ambient thermal energy. The interplay between regolith and solar radiation at high latitudes continues to be a subject of focused study. Even in regions shielded from direct sunlight, charged particles from the solar wind can alter surface chemistry over time. Observations track how these interactions affect the molecular composition of ice and adjacent dust, providing insight into long-term alteration processes. Such measurements expand understanding of surface aging and the chemical evolution of exposed lunar materials, bridging studies of distant planetary bodies with locally collected empirical data. Simultaneously, gravity-assisted orbital studies refine our understanding of the Moon's mass distribution in polar regions. Slight anomalies in gravitational pull influence low-altitude satellite trajectories, requiring precise modeling to maintain stable orbits for observation and future landings. By comparing these measurements with topographic and compositional data, scientists develop integrated models linking mass concentrations, surface features, and subsurface structures. This multidimensional perspective ensures that exploration strategies are informed by a complete, data-driven understanding of the terrain. Analysis of meteoroid flux continues to provide essential environmental context. Instruments on orbiters detect the frequency and intensity of impacts, both at the surface and in the surrounding exosphere. By cataloging the size, velocity, and spatial distribution of micrometeorites, scientists model erosion rates, regolith turnover, and potential risks to both equipment and human explorers. These data inform the selection of protective coatings, landing strategies, and shielding designs, grounding all operational planning in quantifiable evidence rather than conjecture. The Moon's rotational dynamics, influenced by tidal interaction with Earth, are examined with extreme precision. Laser-ranging experiments measure subtle variations in orbital and rotational parameters, confirming the gradual recession of the Moon and the slight deceleration of its rotation over millennia. These findings integrate into models predicting long-term orbital evolution and contribute to comparative studies across the solar system, illustrating how gravitational interactions shape celestial mechanics in measurable ways. The accumulation of decades of data transforms these slow processes from theoretical predictions into empirically verified phenomena. Collectively, the insights gathered from polar studies, gravitational measurements, and impact monitoring emphasize the continuity of lunar science. Each layer of observation, whether chemical, thermal, mechanical, or orbital, builds upon preceding findings to construct a comprehensive and coherent understanding of the Moon as a complex, dynamic system. Rather than isolated facts, these data form an interdependent network of knowledge, enabling ongoing refinement of scientific models and operational procedures. The Moon, approached through disciplined measurement and analysis, emerges as a laboratory where natural processes are not merely observed but quantified, predicted, and integrated into a living scientific framework. As investigations extended to the Moon's regolith, attention turned to its physical and mechanical properties at a granular level. Soil mechanics experiments measured particle cohesion, compaction, and angle of repose, revealing how the powdery surface responds to pressure and disturbance. Observations confirmed that the fine particles cling electrostatically, forming microclusters that influence both dust transport and surface stability. Knowledge of these characteristics guides the engineering of lander footpads, rovers, and surface instruments, ensuring that contact with the Moon does not compromise stability or performance. Researchers also examined how vibrations propagate through the regolith, establishing baseline data for seismic interpretation and equipment placement. Thermal conduction through the regolith became another critical area of study. Layers of dust and fragmented rock respond differently to solar heating, creating a complex profile of temperature distribution with depth. Sensors record diurnal swings in surface and subsurface temperatures, which inform predictive models for equipment operation, instrument calibration, and habitat design. By understanding the interplay between material composition and thermal response, engineers can anticipate challenges in both robotic and crewed missions, tailoring insulation and structural design to the Moon's unique environment. Attention to lunar dust adhesion has proven essential. Electrostatic charging, combined with fine particle size, causes regolith to cling to surfaces, infiltrating seals, joints, and instrument apertures. Experiments quantify how long-term exposure affects materials, how particle behavior shifts under varying illumination and temperature, and how movement during landing, sample collection, or rover traversal alters dust dispersion. Mitigation strategies rely on empirical measurements, such as material coatings and mechanical brushes, translating observational data directly into engineering solutions. The Moon's magnetic anomalies continue to yield insight into its geological past. Detailed measurements reveal localized remnant magnetism in crustal regions, remnants of ancient dynamo activity within the core. These anomalies are cross-referenced with surface mineralogy, crater distribution, and lava flow patterns, allowing researchers to reconstruct sequences of thermal evolution, magnetic field generation, and crustal formation. Understanding these interactions informs models of planetary differentiation and the long-term thermal history of terrestrial bodies, grounded entirely in quantitative observation rather than hypothesis alone. Radiation studies complement these investigations. Instruments measure exposure to solar energetic particles and galactic cosmic rays, providing continuous data for understanding environmental hazards. These readings guide design requirements for shielding and electronics, ensuring that sensitive instruments maintain functionality and that potential crewed operations can proceed safely. Longitudinal data also reveal the variability of radiation intensity over time, tied to solar cycles and transient events, creating a robust empirical record for both immediate planning and predictive modeling. Orbital photometry adds another layer of precision. High-resolution imaging captures albedo variations across the surface, quantifying reflectivity that informs thermal calculations, landing risk assessment, and surface composition mapping. By correlating these measurements with spectroscopic and sample-derived data, scientists create integrated maps that reflect both physical and chemical properties of the terrain. This integrated approach ensures that predictions for surface interactions, thermal behavior, and scientific sampling are grounded in mutually reinforcing datasets, reducing uncertainty across multiple operational domains. Taken together, these studies transform the Moon into a thoroughly characterized environment. Every particle, every thermal gradient, every radiation measurement contributes to a cohesive understanding of lunar conditions. The cumulative knowledge allows not only retrospective scientific analysis, but also proactive planning for future missions, whether robotic, crewed, or observational. The Moon emerges not as an abstract celestial object, but as a precisely documented laboratory, where every action, from landing to sampling to long-term monitoring, is informed by careful empirical study and verified scientific methodology. Expanding beyond surface observations, long-term studies of the Moon's exosphere have revealed subtle interactions between surface materials and space weathering. Trace gases, including helium, argon, and sodium, exist in extremely low densities, but provide measurable information about particle escape, solar wind implantation, and the sputtering of surface atoms. Instruments deployed in orbit continuously track the flux and composition of these particles, creating a dynamic picture of the Moon's tenuous atmosphere. By observing variations over time, scientists gain insight into how solar activity, micrometeorite impacts, and thermal cycling affect the movement of these elements, linking external environmental forces to material behavior at the surface. Simultaneously, rotational and orbital measurements continue to refine understanding of lunar motion. Lunar laser ranging experiments conducted over decades have quantified not only the moon's gradual recession from Earth, but also subtle librations in its rotational axis. These variations influence tidal interactions, long-term orbital stability, and the precise geometry of eclipse events. Continuous measurement validates gravitational models and informs predictions for navigation, satellite deployment, and mission timing, transforming abstract celestial mechanics into quantifiable, actionable data. Investigations into lunar surface reflectivity, or albedo, provide additional insight into material composition and thermal behavior. Observations across multiple wavelengths distinguish regions of fresh ejecta, weathered regolith, and volcanic plains. By analyzing patterns of light reflection, researchers correlate surface features with mineral content, density, and particle size, producing a nuanced understanding of the moon's heterogeneity. This information directly informs both landing site selection and scientific prioritization, ensuring that exploration targets are chosen based on precise empirical criteria rather than visual approximation alone. The mechanical properties of lunar rocks and boulders also remain a subject of ongoing study. Laboratory simulations replicate impact stresses, abrasion, and thermal cycling to understand how these materials respond to both natural and human-induced forces. Data collected in situ from seismometers and contact sensors complement laboratory findings, revealing how geological structures distribute stress and absorb energy. Understanding these properties is critical for vehicle mobility, surface construction, and the deployment of scientific instruments, ensuring that mechanical interactions are predictable and repeatable in the unique lunar environment. Seismic activity, although generally subtle, continues to illuminate the moon's internal structure. Moonquakes, monitored through surface seismometers, reveal the presence of fault lines, fractured layers, and zones of differing rigidity. By analyzing wave propagation, amplitude, and frequency, geophysicists infer the material properties of the crust and upper mantle. These findings inform models of stress, accumulation, thermal contraction, and structural evolution, demonstrating how even minor seismic events contribute to a broader understanding of planetary mechanics. Long-duration environmental monitoring has also focused on solar and cosmic radiation effects on the surface and near-surface materials. Instruments measure particle flux, energy deposition, and secondary radiation resulting from particle interactions with regolith. This empirical data informs predictions about material degradation, dust charging, and the potential for radiation-induced chemical changes over time. By grounding these models in repeated measurement, scientists can anticipate environmental hazards with precision and incorporate these factors into both experimental design and long-term mission planning. Taken together, these investigations extend the scientific record of the Moon beyond a single mission or set of observations. They encompass the behavior of particles, rocks, and instruments under a range of conditions, the interaction of surface materials with solar and cosmic energy, and the precise motion of the Moon relative to Earth. Each measurement, each observation builds upon prior knowledge, reinforcing a coherent understanding of the Moon as a complex, measurable, and continuously evolving system. The Moon becomes, in essence, an enduring laboratory of planetary science, one where the application of careful observation, rigorous measurement, and empirical validation produces an ever-deepening understanding of our nearest celestial neighbor. Attention to the Moon's thermal environment has deepened with continuous monitoring of surface and subsurface temperatures. Radiometers and thermal sensors measure how heat from the Sun penetrates layers of regolith and interacts with rock formations. These readings reveal gradients in conductivity, density, and composition that vary across plains, crater floors, and slopes. By understanding these differences, scientists can predict how heat will accumulate or dissipate over time, informing the design of instruments, habitats, and energy management systems for both robotic and potential crewed missions. The study of micrometeorite impacts provides another crucial layer of understanding. High-frequency sensors record collisions with particles small enough to be invisible to the naked eye, but capable of altering the surface over time. By quantifying impact, velocity, frequency, and distribution, researchers track regolith turnover, erosion rate, and the creation of secondary ejecta. These observations allow accurate modeling of surface evolution, guiding both landing safety assessments and the long-term durability of equipment deployed on the Moon. Investigations into the Moon's gravitational field continue to refine knowledge of mass distribution beneath the surface. Detailed gravimetric mapping detects mascons and subtle density variations, providing insight into the internal composition of crustal and mantle structures. Understanding these anomalies enables precise orbital planning, satellite stability, and prediction of tidal interactions. By linking gravitational measurements with surface topography and mineral composition, scientists construct integrated models that relate internal structure to observable features, grounding geophysical theory in tangible, measurable evidence. Solar-wind interactions remain a key area of research, particularly regarding their effects on the regolith and near-surface environment. Ion implantation and sputtering gradually alter surface chemistry, embedding charged particles into mineral matrices and modifying reflectivity, conductivity, and chemical composition. Instruments analyze these modifications over time, connecting space weathering processes to measurable changes in material properties. These studies not only illuminate the Moon's ongoing evolution, but also serve as analogues for understanding similar processes on other airless bodies, from Mercury to asteroids. Subsurface radar studies complement surface investigations, probing the stratigraphy beneath regolith and rock layers. By transmitting and analyzing electromagnetic waves, scientists map variations in density, detect buried structures, and estimate layer thicknesses. Data from radar surveys allow reconstruction of impact sequences, lava flow depth, and depositional history, producing a three-dimensional view of the lunar near-surface environment. Such detailed information enhances predictions for stability, resource availability, and scientific sampling strategies, all grounded in precise, replicable measurements. Cumulative data from these diverse studies converge into a detailed, multi-layered understanding of the Moon. Surface composition, regolith mechanics, thermal dynamics, seismic activity, gravitational anomalies, and space weathering are all interconnected, forming a coherent scientific framework. Each observation informs the next, creating a continuous chain of validated knowledge. The Moon emerges as a meticulously quantified environment where phenomena are described, measured, and predicted with precision, demonstrating the power of sustained empirical investigation. In reflecting upon this extensive body of research, the Moon becomes more than a distant celestial object. It is a dynamic laboratory, a record of planetary processes, and a source of continuously evolving data. Every measurement, from microscopic regolith behavior to orbital mechanics, adds to a comprehensive understanding built on observation, calculation, and verification. The scientific legacy of lunar exploration ensures that knowledge of the Moon is both reliable and enduring, offering a foundation for ongoing discovery, technological development, and methodical inquiry. Attention to lunar sample analysis has continued to yield precise information about the Moon's chemical and isotopic composition. Advanced laboratory techniques such as mass spectrometry and X-ray diffraction identify elemental abundances and mineral structures at microscopic scales. By comparing isotopic ratios of oxygen, titanium, and other elements with those found on Earth, scientists have refined models of the Moon's origin, confirming that it formed from material ejected during a giant impact early in the solar system's history. These data also clarify the differentiation of crust and mantle, revealing subtle heterogeneities that inform models of thermal evolution and magmatic activity over billions of years. The study of lunar regolith chemistry has expanded to include volatile compounds and implanted solar particles. Analysis of trapped helium, neon, and hydrogen provides insight into the accumulation of solar wind over time, while the detection of water-related molecules informs hypotheses about volatile retention and migration. Techniques such as secondary ion mass spectrometry allow scientists to examine particle surfaces at submicrometer scales, revealing how individual grains interact with cosmic radiation, thermal cycling, and micro-impacts. These empirical observations bridge surface processes with broader questions of planetary evolution and space weathering. Isotopic studies also provide chronological context. Radiometric dating of rock samples and impact melt sheets establishes absolute ages for geological events, such as mere volcanism and major impact episodes. Cross-referencing these ages with crater density measurements enhances the accuracy of lunar chronology, providing a temporal framework for surface evolution. The integration of sample-based dating with orbital observations allows scientists to model not only spatial distributions of geological features, but also their historical development, producing a timeline of lunar processes grounded in reproducible measurement. High-resolution imaging of surface textures contributes additional scientific insight. Microscopic examination of soil and rock surfaces reveals the cumulative effects of micrometeorite impacts, thermal expansion and contraction, and solar wind sputtering. These features inform interpretations of regolith maturity, particle formation, and surface renewal processes. By documenting variations in grain shape, layering, and reflectivity, researchers gain quantitative evidence of ongoing geological and space weathering mechanisms that continuously modify the Moon's exterior environment. The Moon's internal structure continues to be elucidated through geophysical methods. Seismic and gravity data, combined with modeling of tidal deformation, reveal the thickness of the crust, the density profile of the mantle, and the properties of a small, partially molten core. These findings confirm that the Moon, although geologically inactive compared to Earth, retains distinct layers that respond to both internal stresses and external gravitational forces. Understanding this internal architecture is essential for predicting the behavior of the surface under natural and human-induced loads, such as lander contact or future construction. Radiation monitoring has documented long-term exposure patterns across multiple solar cycles. Instruments measure fluxes of high-energy protons, electrons, and heavier ions, enabling precise calculations of cumulative dose for both materials and potential human presence. By correlating these measurements with solar activity and orbital position, scientists develop predictive models for radiation hazards, directly informing the design of protective systems and operational protocols. This data emphasizes the dynamic interaction between the Moon's environment and external cosmic influences, reinforcing the empirical foundation of lunar science. Taken together, the integration of chemical, isotopic, structural, and environmental studies reinforces a comprehensive, data-driven understanding of the Moon. Each measurement, whether derived from surface samples, remote sensing, or orbital observation, contributes a unique perspective that enhances the overall scientific picture. The Moon emerges as a fully characterized system, where physical processes are observed, quantified, and interrelated, allowing both retrospective analysis and the planning of future exploration with confidence, grounded entirely in empirical evidence. The integration of orbital and surface measurements continues to refine understanding of the Moon's geological diversity. Remote sensing instruments detect variations in mineralogy and topography across mare basalts, highland regions, and impact craters. By combining spectral data with high-resolution imaging, scientists map compositional heterogeneity, correlating surface features with underlying geological structures. These mappings allow for predictive models of terrain, mineral distribution, and regolith characteristics, supporting both scientific inquiry and operational planning for future missions. Empirical observations establish a consistent framework that links remote data with in-situ analyses, confirming the reliability of interpretations across multiple observational platforms. Seismology on the Moon remains a critical tool for probing its interior. Even low-magnitude events generate waves that traverse the crust and upper mantle, enabling the reconstruction of structural layers. The velocity, amplitude, and attenuation of these waves provide direct insight into material density, elasticity, and fracture networks. When combined with gravity data and geological mapping, seismic information enhances models of tectonic stress, crustal heterogeneity, and the history of internal cooling. Each event, catalogued and analyzed, reinforces a cohesive understanding of lunar geophysics that continues to evolve with ongoing measurement. The study of lunar volatiles extends beyond surface deposits to encompass interactions with the exosphere and solar radiation. Instruments detect transient outgassing, trace elements, and the migration of particles influenced by thermal gradients and electrostatic forces. By observing these processes over extended periods, scientists quantify the rates of volatile redistribution and loss, establishing a dynamic model of lunar surface-atmosphere interaction. These findings provide context for resource utilization, environmental modeling, and comparative planetology, demonstrating how empirical data informs both applied and theoretical understanding. Investigations into regolith compaction and layering reveal the mechanical history of the lunar surface. Stratigraphic analysis of core samples and trench exposures shows the cumulative effects of impacts, thermal cycling, and micrometeorite bombardment. By measuring particle orientation, density, and cohesion at various depths, researchers assess the mechanical integrity of the regolith and its response to applied forces. This information informs the design of lander footpads, rover wheels, and potential structural foundations, ensuring that human and robotic activities are compatible with the natural properties of the terrain. Laser ranging experiments continue to provide precise measurements of the Moon's distance and motion relative to Earth. By reflecting laser pulses off retroreflectors left during previous missions, scientists calculate the Earth-Moon separation to centimeter accuracy. These data confirm the Moon's gradual recession, orbital librations, and subtle variations in rotation, offering continuous verification of gravitational models. The persistence of these measurements over decades demonstrates both the reliability of instrumentation and the precision achievable through systematic observation. The integration of these diverse datasets creates a multifaceted understanding of the Moon as a dynamic yet predictable system. Chemical composition, structural integrity, thermal response, orbital behavior, and environmental conditions are interrelated through empirical observation, forming a cohesive framework that supports both current knowledge and future exploration. Each observation corroborates others, establishing a network of validated information that ensures continued accuracy and scientific rigor. Through this cumulative approach, the Moon emerges as a laboratory of planetary science, where every measurement, from microscopic particle analysis to large-scale orbital monitoring, contributes to a continuously evolving understanding. Observations are interconnected, reinforcing and refining one another, and each layer of data provides context for subsequent investigations. The Moon's environment is quantified in detail, allowing predictions and planning to rest firmly on observable, reproducible phenomena. Scientific inquiry here is deliberate, methodical, and sustained, producing a legacy of knowledge that persists far beyond any single mission or dataset. The Moon's surface continues to reveal subtle variations in albedo and texture, measured through high-precision photometry and multispectral imaging. By observing how sunlight interacts with different regions at varying angles, scientists determine the reflective properties of soils, the presence of fine dust, and the degree of space weathering. These observations allow for refined models of thermal absorption and radiation, which in turn inform predictions about temperature fluctuations and energy management for instruments and habitats. Each reflection, each variation in brightness, is a quantifiable signal that contributes to a precise understanding of lunar environmental conditions. In tandem, gravitational studies refine models of the Moon's internal mass distribution. High-resolution gravimetry detects minute deviations in the gravitational field, revealing concentrations of denser material beneath the surface and confirming the presence of mascons. When combined with topographic data, these measurements elucidate correlations between surface features and subsurface structures, enhancing predictive models for satellite orbits and informing strategies for landing site selection. Each data point strengthens the ability to forecast mechanical and navigational behavior with accuracy rooted in observation. The persistence of micrometeorite bombardment shapes the surface on scales both large and minute. Continuous monitoring of impact frequency and particle velocities allows scientists to quantify erosion rates and track the evolution of regolith depth and composition. analysis of crater density and distribution, coupled with radiometric dating of return samples, produces a temporal map of lunar surface modification. These findings provide not only historical context, but also practical insight for protecting instruments and future installations from cumulative surface disturbances. Subsurface radar studies extend this understanding beneath visible layers. By transmitting electromagnetic waves and analyzing reflections, scientists map the thickness of regolith, detect buried lava flows, and identify subsurface stratigraphy. The data reveal patterns of layering that record the Moon's geologic history, from volcanic episodes to impact events, creating a three-dimensional picture of the near-surface environment. Such information informs both scientific inquiry and engineering decisions, ensuring that exploration strategies are aligned with empirical evidence. Thermal dynamics remain a central focus, particularly the interaction between solar radiation and material properties. Sensors track diurnal temperature variations at multiple depths, revealing how heat penetrates regolith layers and dissipates into the underlying crust. The resulting thermal profiles inform models of surface stability, structural integrity, and energy management for equipment and habitats. These observations connect the physical properties of materials with their environmental context, providing a detailed and actionable understanding of conditions across the lunar surface. Taken together, these studies contribute to a comprehensive and continuously updated model of the Moon. Each measurement, whether of light reflection, gravitational fluctuation, impact frequency, subsurface layering, or thermal behavior, reinforces the broader scientific framework. Observations are integrated to form a cohesive picture of the lunar environment, where surface and subsurface processes, energy interactions, and mechanical properties are all quantified, linked, and understood. The Moon, once distant and enigmatic, is revealed as a systematically documented laboratory where natural phenomena are measured, monitored, and contextualized with meticulous precision. This accumulation of knowledge demonstrates the enduring impact of empirical observation and scientific rigor. The Moon's environment is approached not through speculation, but through sustained, repeatable measurement. Every layer of data, from the fine regolith to deep interior structures, informs subsequent research and operational planning. Through decades of observation, analysis, and verification, the Moon emerges as both a destination and a resource, a record of planetary history, and a laboratory for understanding fundamental processes that govern celestial bodies throughout the solar system. Studies of lunar dust transport have further enhanced understanding of surface dynamics. Electrostatic forces, generated by solar radiation, cause fine particles to levitate and migrate across the regolith. Observations using optical sensors and dust detectors quantify the height, distribution, and frequency of particle movement, revealing patterns that depend on local topography, illumination, and solar activity. These measurements are essential for anticipating operational challenges, such as contamination of instruments, interference with mechanical systems, and the gradual alteration of surface features over time. Dust behavior, while subtle, has measurable consequences for both scientific experimentation and practical engineering. The examination of lunar magnetic anomalies provides additional insight into the Moon's geologic history. Localized crustal magnetism, mapped through satellite magnetometers, correlates with ancient impact basins and volcanic formations. By analyzing the intensity, orientation, and distribution of these magnetic signatures, scientists infer the presence of remnant dynamo activity and variations in crustal composition. These findings complement surface geology, offering a three-dimensional perspective on the formation and evolution of lunar structures, grounded in empirical measurement rather than conjecture. In parallel, laser altimetry has refined topographical models with sub-meter accuracy. By precisely measuring the time delay of reflected laser pulses from orbiting satellites, scientists construct detailed elevation maps that reveal subtle slopes, crater rims, and ridge networks. These data inform landing site selection, hazard assessment, and surface navigation for both robotic and potential crewed missions. Elevation measurements, integrated with compositional and mechanical data, produce a comprehensive spatial understanding that is essential for operational planning and scientific interpretation. Solar-wind interactions with the lunar surface continue to be characterized in detail. Ion detectors and particle analyzers measure implantation rates, sputtering effects, and the generation of secondary particles. These observations reveal how surface materials are chemically and physically altered over time, influencing reflectivity, thermal behavior, and even the retention of volatiles. By quantifying these processes, scientists link environmental exposure to measurable changes in surface properties, enabling predictive modeling of lunar material behavior across extended periods. Finally, cumulative orbital data inform models of long-term orbital evolution and tidal interaction. Continuous monitoring of the Moon's position, rotation, and libration, combined with gravitational measurements, allows precise calculation of its recession rate and subtle oscillations. These data not only refine celestial mechanics, but also ensure that planning for satellite deployment, communication networks, and navigation remains anchored in empirical verification. The Moon's motion, measured over decades, becomes a predictable and quantifiable phenomenon, reinforcing the broader framework of observed physical laws. Taken together, these strands of research, dust transport, magnetic anomalies, topography, solar-wind interactions, and orbital mechanics, form a tightly integrated scientific narrative. Each layer of measurement informs and validates others, producing a coherent, continuously evolving model of the Moon as a precisely documented environment. Observation, analysis, and empirical validation converge to create a comprehensive understanding in which every measured phenomenon contributes to a holistic depiction of our celestial neighbor. In this enduring pursuit, the Moon is no longer a distant point of light, but a thoroughly explored and quantified laboratory. Its surface, interior, and orbital dynamics are documented with meticulous precision, revealing the interplay of geological, physical, and environmental processes. The knowledge gained through decades of careful study provides a foundation for continued exploration, ensuring that future missions proceed with confidence rooted entirely in observation, measurement, and scientific rigor. The Moon, in its silent orbit, stands as a testament to methodical inquiry and the accumulation of enduring empirical understanding. As we draw the narrative to a close, it is worth pausing to reflect on the Moon, not as a distant, mysterious object, but as a rigorously studied, thoroughly measured environment. Every particle of regolith, every crater, every subtle fluctuation in orbital motion has been catalogued and analyzed. Instruments continue to record radiation, temperature, and dust movement. Samples reveal elemental and isotopic compositions, and orbital measurements track gravitational and rotational nuances with exacting precision. This continuous accumulation of empirical data transforms the Moon into a laboratory where natural phenomena are observed, quantified, and understood in their full complexity. Through decades of careful observation, the Moon has become a testament to the power of methodical inquiry. It demonstrates how patience, precise measurement, and systematic study can convert a celestial body into a source of enduring knowledge. From the fine grains of its regolith to the deep structure of its interior, from the faint movements of dust to the subtle oscillations of its orbit, each observation contributes to an integrated understanding that is both practical and profound. The Moon, silent and distant, offers insights that reach across time and space, informing not only science, but also the planning and execution of future exploration. Lying beneath the quiet night sky, one can imagine the Moon not as a point of light, but as a complex, measured world, continuously revealing its secrets through careful study. Every measurement has its place. Every observation contributes to the whole, and the result is a coherent and precise understanding of an environment once shrouded in uncertainty. This knowledge provides both reassurance and inspiration. Reassurance that the processes of science can produce certainty, and inspiration for the human mind to continue observing, questioning, and exploring